Okay. Hello, I'm Wonjun Jo, a PhD student at AMIREP. Today I'll talk about latent video wall models, present and future. The title is a bit ambitious, right? So today I'll introduce the recent advance in wall models, especially latent video wall models, and discuss how this research may evolve and what direction are meaningful at lab level. So I'll skip too much technical detail of the research. So since I also want to hear your thoughts, so please take this as a light discussion. Okay. I mentioned wall models briefly last seminar. So today I'll explain the idea again briefly. The wall models, wait a minute. Well, wall models are inspired by how human cognition works. Our brain doesn't process every detail of the world around us. So instead, it uses mental models. This is the simplified pattern from past experiences to make a quick decision in complex situations. So even before event happens, our brain relies on this model and past actions and their outcomes to predict what's coming next. If we apply this idea to AI, the agent doesn't need to learn by acting in the real world. So it can use a wall model to simulate possible future events. And by simulating inside, AI can try many behaviors without doing them for real, which reduce the resources. And also, wall model predict the words, how the word evolves. So word model also have the very strong generalizable ability. The important milestone paper is wall model in years 2018. This work applies this to the reinforcement learning paradigm. The observation passed through VA to get latent Z. This is the scene representation. And RNN combines this with the past information, H, and the controller outputs the output actions. Then one model is trained by reinforcement learning with viewer from action, and the changed environment provides a new input and process is repeated. And how about recent role models? Here are two recent generative one models. First is Cosmos Predict 2 from June 2025. It generates visual world by combining videos and text inputs. Second, Genie 3 from August 2025. It generates visual world conditioned on action, these actions, and text. This model show how word models are moving beyond pure prediction to reach generative simulations. So generative world models are strong because they produce realistic simulations, but they are expensive, requiring the massive data, compute, and often modeling irrelevant pixel level details. For reasoning and long-term prediction, we don't always need such fine detail. This is why latent wall models emerged. They skip the unnecessary low-level generation and instead learn compact latent states that capture only the essential structure and dynamics of the world. This makes them more efficient while still supporting powerful prediction and planning. So I bring the two recent latent wall models. First is the V-JEPA 2, pre-trained on large-scale videos to run dynamics and fine-tunes with small level data for efficient planning. And second one is DINO-World. This one builds on strong DINO features to model temporal dynamics and extend with the small action data to plan without heavy training. Let me briefly introduce these two studies. First is the V-JEPA 2. This is from Meta. The motivation is real-world level interaction data is very scarce and expensive to collect. To scale video world models, V-JEPA 2 takes a different approach. It uses a self-supervised paradigm that combines massive internet scale data, video, with only a small amount of robot data. This way, the model can learn general world dynamics from large video corpora and then adapt to robot tasks with limited demonstration. So V-JEPA 2 scales up the JEPA framework. JEPA framework just means the self-supervised learning, one of them, with more than 1 million hours of internet video and images. Through self-supervised pre-training, it supports strong understanding and prediction across tasks like video QA, object recognition, action anticipation. Then with small amount of robot data, the model can be fine-tuned to enable planning in real robots in zero-shot way. So in the first stage, V-JEPA 2 is pre-trained on internet scale video without using any action labels. The model learns by masking by parts of input frames and predicting them back in the latent space, not in the pixel space. This self-supervised pre-training builds a strong video representation that captures temporal dynamics before any robot data is introduced. In the second stage, V-JEPA 2 is post-trained with a small amount of robot action data, about 62 hours from the Droid robot dataset. The video encoder is kept frozen. This is frozen, and action condition predictor is trained by injecting robot actions and poses. This step allows the model to go beyond passive video prediction and enables planning and control in real robot setting. This is the overall pipeline. So first, self-supervised learning is done, and then with the small scale robot data, encoder is frozen and the predictor is learned. This JEPA world model is just the predictor, as I mentioned. And then in the planning stage, the model imagines possible future states and compares them to a global image in the latent space. This global image is given in these scenarios. So it plans by minimizing the error distance between the imagined future and the goal. And to find the right sequence of actions, it samples multiple candidates and keeps the top K and average them to produce a final action plan. This figure shows the single goal reaching task. The robot arms start from an initial pose and moves toward the goal frame using the V-JEPA 2 planner. The graph shows position error decreasing over step in X, Y, Z directions. This confirms that the model can plan actions to reach the target. And this is the comparison. Octo is just state-of-the-art robot manipulation work. So Octo succeeded only about the 25%, while V-JEPA 2 AC means the action condition. This is post-trained V-JEPA 2, reached the 65 to 80%. And Cosmos is generative world model, as I mentioned before. So Cosmos needs 4 minutes per action, but V-JEPA 2 with more samples planned and in just 16 seconds and outperform. The number of samples mean when this model predict one action, they can sample these number of samples. Yeah. And also V-JEPA 2 consistently outperforms the prior video encoders. both motion and appearance understanding. And also V-JEPA 2 on action anticipation, V-JEPA 2 achieved clear state-of-the-art, especially with the largest model. To conclude, V-JEPA 2 scales the joint embedding predictive architecture. This is just a self-supervised learning method with massive video data and a small amount of robot data. It achieves state-of-the-art result in understanding and prediction, and with action conditioning, it even enables zero-shot real-world robot planning. Okay, then I'll introduce the second paper, back to the features as a foundation for video world models. This model is just called by DINO-World. This works motivation and contribution is almost same with the V-JEPA 2. So motivation is pixel-based generative models are heavy and waste effort modeling unnecessary details. DINO-World instead focus on efficient latent models building on strong pre-trained features like DINO-V2 without the pixel level prediction. So here the contribution is clear. Author introduced the DINO-World, a latent video world model built on a frozen DINO-V2 encoder. It is trained at scale on more than 60 million web videos to capture the broad temporal dynamics. Okay, there's a method. Pre-training in DINO-World can be divided into two steps. First, each past and future video frames are encoded with a frozen DINO-V2 model to obtain strong visual features. Second, the predictor network. This is just cross-attention net blocks. A predictor network learns to take past features as input and predict the latent features of future frame. The training objective is to minimize the difference between predicted and actual features, all in the latent space. I'll skip the too much detail of this. And in the fine-tuning stage, they add a small amount of action data in the form of observation and action pairs. The predictor is extended with the action block, simple action block. So the future features can be predicted conditioned on both past observation and action. This enables the model to perform planning and control tasks. So there's a result. This table compares DINO-World with several baselines from trivial copy, just trivial copy version, and to the large generative model like Cosmos. DINO-Foresight is just a predictive model similar to DINO-World, but trained with a mask reconstruction objective on just a limited domain, like autonomous driving. The column correspond to dense forecasting tasks, VSPW and cityscapes for semantic segmentation accuracy, and Kitty RNSC for depth prediction. So DINO-World shows strong performance, but note that the DINO-Foresight performed better on cityscapes and Kitty, mainly because it was trained on autonomous driving domains. So DINO-World has the general overall great results. And this table shows result on 3 intuitive physics benchmarks. In-piece test whether model can distinguish physically possible from impossible video events. Graphs evaluate both language grounding and intuitive physics understanding. And inf level is inspired by infant cognition, measuring the surprise and continuity, solidity, and gravity, and violated. Looking at the results, the Cosmos achieved highest score in implies, meanwhile, DINO-World achieves strong and balanced performance on graphs and input level. Here is the qualitative result of DINO-World. Here, they visualize autoregressive prediction of the DINO-World model. The top row shows the input image frames. The middle row is the encode feature by this RGB image. And bottom row, the model's predicted features in latent space. So for the first frames, the model has assessed the ground truth feature, this one. And afterward, it must predict into the future by feeding back its own outputs, this autoregressively. In the traffic scene, the model correctly tracks the taxi turning at the intersection, showing a common sense understanding of driving. And in the physics scene, it accurately follows this linear moving, these green balls, and parabolic motion of this silver ball. Overall, this green ball is tracked on the feature space. This is a ground truth features, pseudo ground truth features, and this is the autoregress feature. The autoregress feature is almost correctly tracked these features. Overall, the figure highlights the model's ability to capture context and predict meaningful future dynamics in this latent space. And this is the result on simple planning tasks. First, in the Scratch setting, the predictor and action blocks are trained from Scratch. Second is the seconds. In the action-only setting, the pre-trained predictor is frozen and update only the action blocks. Finally, fine-tuning setting, start from pre-trained predictor and update all predictor and action block parameters. So briefly, the takeaway is that large-scale pre-training, in these cases, combined with the fine-tuning of the predictor and action block is crucial for strong planning performance. But I think this result are expected, but the lack of strong baselines makes the comparison less compelling. There's no baselines, actually. So conclusion is DINO-World is a latent space wall modeling, avoids predicting the irrelevant pixel level details, and using the frozen DINO-V2 encoder with strong semantic features, and also achieve the general great performance on various downstream tasks, including the planning task. So this is a summary. V-JEPA 2 and DINO-World commonality is both latent wall models learn dynamics in latent space without pixel level prediction and aim to scale video understanding and planning from large video data. And differences is just a loss, naively the loss is the difference, and also V-JEPA 2 pre-trains from scratch on internet scale data and then fine-tunes with small local data. And DINO-World used the frozen DINO-V2 pre-trained encoder to guide the strong and reliable features. Okay, this is the end of these two papers. And there's also limitation on latent wall models. I think the latent wall model also are still resource heavy because training requires a large data set and high GPU memory, like 60 million videos, especially for long temporal context and also the latent is so abstract and hard to interpret. So latent features are ambiguous, making debugging and verification is difficult. And also the input there is no physical grounding. Semantic features don't directly capture the physical properties like mass, friction, and contact. So, and then there's my future direction. This is just my early stage of my thoughts. So to wrap up, let me link the limitation to the future directions. First, efficiency remains challenges. So starting from strong pre-trained encoders like DINO-V2 and DINO-V3 can help. Second, the latent world model lacks detailed physics. So lightweight supervision and coarse cues like friction, mass could improve the grounding without costly simulation, like all pixel simulation. And finally, current latent are constrained and ambiguous. So instead of ambiguous continuous latents, discrete and compositional representations are more interpretable. So this connect to this work related to slot attention in URIS 2024, which decompose the scene into object-centric slots, and shows how top-down signals can guide the structured latent representation. And when this model is trained, each code represent this object level semantics. Okay, this is my end of the presentation. Thank you. Record.